getting distracted and not getting done. All right, so that part is done. And double check the recording is actually from the microphone. It's all good. Let's see what else. We need a subfolder today. Trust me, we're gonna need a big subfolder today because you're having your first homework assignment that actually has something to do with programming. Yay! You guys are not very enthusiastic about that.
It's kind of late.
All right. So let's go ahead and look at, well, this is already past due, so, oh, that's not good. If it keeps this up, we have a problem. Uh-oh. That is not good.
Well, it's past 7.
Okay, there we go.
It's past 7.
Well, that might happen because we have 2 psychology professors using some profs too. And, yeah, 2 psychology professors, and they're teaching Psych 300, 370, some of the other classes. And guess what? I have 0 issues from the psychology students. The psychology students use it for forums. They have heavy use of the forums. Turn in homework assignments, take the quizzes and whatnot. I have had 0 issues with the psychology professors or their students, which is interesting. I would say that's pretty interesting. They generate, the 2 psychology professors generate maybe 4 times the traffic of 8 CIS professors. Because they have forums, they have active discussion and they use it for grading purposes. Those are fully online classes. I'm only using Moodle to like collect homework assignments and organize my teaching material. But you guys, for the most part, we are not. This is not an online class. I mean, obviously, looking at the classroom right now, I think some people are thinking this is an online class. Look at all the empty seats, All right. So this is your homework assignment, and I don't think we have to go over this too much. I'm going to write the program to grade it automatically, assuming everybody turned in something that my program knows how to read, conforming to the standard. So here's your new homework assignment. It's just simply called MEM1, and the format of the homework assignment. This is going to be something that is very common to all our homework assignments. The first thing you have to do is to download a file, okay, put it into the home folder of your Linux account, decompress it, it will turn into a folder by itself, and then your homework is inside that folder. Okay, it usually starts with 1 file. At some point, I will start with multiple files. So let's go ahead and do this part. I'm just going to demonstrate exactly how to do it. When you use a virtual machine, you have to do one more step, which means you have to download this in Windows and then upload it using WinSCP into the virtual machine. Okay? But since I am using Linux, it's a really easy process. So I'll just go ahead and download this to, okay, I'm going to create a folder for that. Just so, oh, wait, I can do it inside today's folder. Even better. All right. So now I have the archive file downloaded. And switching back to my command line prompt, I can now do an ls, and sure enough, we have the file downloaded into this folder. So from now on, I'm pretending that this folder is your home folder. So you have to do it in your home folder. I'm using this as like a pretend home folder from this point on, so that if you want to upload the whole thing, you can download the whole thing after the class too. So the command to decompress is tar xzvf. The v is not really required, but this way it shows you what files are getting created and so on. If not, I usually keep the v option, and you just give it the file name. But you have to do it inside your home folder because the file should be placed in your home folder. Okay. Any questions at this point? No questions? Press the enter key, magic happens, we have a new folder, and inside the folder we have a file. So the next thing you want to do is to use cd to change into that folder, ls to confirm that we do have that one single file that you have to start with. And then you can use your favorite editor in Linux, or if you use WinSCP, WinSCP can open a text file on a remote machine as if it is opened locally. So for those of you who don't want to learn anything about Linux, you can actually use WinSCP as a use the editor built into WinSCP for homework purposes. You lose all the syntax highlighting, you lose a lot of the capabilities of VI and a more capable editor doing it that way. Okay, here's the program, and just to try to entice more people to switch to VI, here's this syntax highlighting, different colors, and it's all good. All right, this is your first program, and we will explain this kind of junk later on in this class. But your homework assignment is really this part here. That's the description of your homework assignment. I'm just going to read it a little bit here. You can only write 2 instructions. Your first programming assignment has 2 instructions. But I'm putting a very severe, a big restriction here. You cannot use any immediate operands. Immediate, okay. I was just checking my spelling. Okay, VI doesn't have spell check. Okay, so you cannot use any immediate operands. By only using 2 instructions, I want EAX to end up with a value of, this is a decimal number, so it would be 5,452,593. That's the exact value that I want to be in EAX after your 2 instructions. Okay? Do not change any part of this program. In other words, you cannot change these things. You cannot add any additional definition. You cannot delete any existing definitions. Do not do anything other than inserting your 2 instructions into this program. Okay? Any questions about the restrictions? Yes?
2 instructions means there's 2 lines?
2 lines of actual code. You can have additional lines for comments if you want to. Okay, I'm suspecting that some of you would want to insert your own comments so that you can actually figure out step by step, how to get this done. Okay. All right. Easy enough? Sort of. Yes.
The 2 lines has to be in before and after.
The 2 lines have to be here, as in open a new line. Oops. Here. So put your instructions here. Okay, between the label before and after, after the label before and before the label after. That's confusing. Yep. Those labels are here so that my grading script can automatically put a breakpoint before your code and after your code so I can check stuff automatically. Okay? See, I want to automate everything whenever it is possible. But I will still read your program, so don't feel that you are left out, that this is all a mechanical process. I will read every single program manually just to see how people write the program, identify potential issues and stuff like that. Right? Are we doing okay so far with the instructions of the homework assignment? Okay. Now reading on to the rest of the program, the assignment description here. When you are done with mem1 as the current working directory, CWD stands for current working directory, execute the following command to create the submission tar file. So this is what you turn in. And since I'm in Linux right now, I can just copy and paste it, and then press the Enter key. This is exactly what you should see as a message. It will give you like a warning message that says removing leading / from member names. That's fine. It's not an error. It's just complaining that when you specify a path to tar, it should not start with a /. That's all it's saying. Okay. And after that, we have a file, the new file created. What did I do wrong here? Oh, it was created into my home folder. So if I look at my home folder, which is represented by the tilde symbol, I should find that file. Okay, and that's the file that you have to turn in as your homework assignment submission. Is that okay so far? All right. Now, this is the important part. We'll probably come back to this, again and again today, just to make sure that we cover all the concepts that we need in order to do this homework assignment. So this homework assignment is going to exercise all of these concepts, and you have to learn these concepts and be able to apply these concepts in order to successfully do this homework assignment. First is how is memory organized and initialized. Okay? First thing we'll look at is that. The second one is Little-Endian. Okay, what is Little-Endian versus Big-Endian? The third one is to use the use of the direct addressing mode, something that we have not talked about yet on Tuesday, because on Tuesday we ended with the discussion of the register operand and also the immediate operand. Okay? We need to understand the use of register operands. We need to understand how registers are organized. We talked about that already. And a student visited me today and asked me for some clarifications, and I think the questions were excellent. And so just to summarize what I told this particular student, AL, AH, AX, and EAX, they're basically defining windows, different sizes of windows and potentially at different places into the same physical register. There's only one physical register called register A, which stands for accumulator. AL is a very small window, it's an 8-bit window to only look at the least significant 8 bits of that one register. AL is also an 8-bit window to look into this 32-bit register, but it is not looking at the least significant 8 bits, it's looking at the second least significant 8 bits. To name the bits, it's bit 8 to bit 15 because we come from 0. AX is a slightly larger window into this register. It looks at the least significant 16 bits of a 32-bit register. EAX is the full view of the 32-bit register. Is that okay? I mean, is that helping a little bit? Okay. So AL, AH, AX, and EAX are basically just different windows, different portals to look into the same physical register that we call register A. Yep.
When I was on my computer and I was running the example that you did Tuesday, when I ran GDB and printed out like the values at the registers, whenever I did BH or BL, it would say void, and I could only access like the value by looking at the entire register.
Okay.
Do you know anything about that? Or?
When we get into GDB, we might need to take a look at that. Okay, so maybe it only works for register A. Did you try it with AL and AH?
Yeah. I
Did
tried
that work?
No, it didn't.
That did not work.
Yeah,
okay.
it still said void every time. Unless I did the entire
We'll
register.
look into that. Do you have a Debian installation or do you have a
Yeah,
different
it was a
installation?
virtualized Debian on an
Okay. We'll take a look at that.
Okay.
Yep. So that's what we are up to this point here. Then we'll talk about what a label really is, okay? Because it is very essential for people to remember to understand what a label is and is not in this class. We'll definitely figure out how to use the debugger. There will be new commands that we'll be talking about in the debugger that will be of a lot of help for your homework assignments. How to do base 16, 8, and 10 conversion. You can use a calculator, that part is really not very, very important. And also, the last part is a label is not a variable, and repeat it 20 times. Because somebody is going to think, oh, this is a variable. No, it is not a variable. And this assignment will make it extremely clear that a label is not a variable. Okay? Shall we get started? Okay, very good. We'll start with how memory is organized. We'll start with that, okay? So what we'll do is we'll make a very simple program, and we'll just say, I'll call this mem0, okay, because it precedes the homework assignment. You should really understand this one before you even try the homework assignment. Okay, so we'll start with the usual stuff. I don't have anything that I need to change over time, so everything can go into the text segment or the text section. We have to declare global underscore start is a global, which means the linker can now see it. Otherwise, it would just complain about it. And we'll start with a label definition. We'll start with L1 as a label, very plain and simple name. And then we'll just kind of put some random structures here. We'll say, we'll start with .fill 5, and then we'll say .byte. Okay. Now after .byte, I will specify the values of the bytes that will be initialized. But I will try different formats. In other words, I'll try different bases to specify that value. 45 is in decimal. 045 is an octal number. 0x45 is a hexadecimal number. And we'll just throw in a binary number because you can actually specify binary numbers inside the assembler. So we'll just give it a, oops. Okay, we'll just give it a kind of random sequence here. All right, and we'll throw in an ASCII. In other words, we'll throw in a string here. We'll just say tag here, and then we'll throw in, say, a .int. And curiously, we'll throw in almost exactly the same thing. But we'll see how everything is going to be organized in memory. Okay. Let's see, what else should we throw in here? Maybe throw in a .ascii's, okay, with my last name. I think that's good for now. So here's my program, the entry point of the whole program. And the program is not even important. I will just specify the Ascii code here, just as a good habit, because for the most part I won't even run the program. I just want to look at how memory is going to be organized. All right, that's my whole program, my demonstration program, and that has everything to do with your homework assignment. Okay, well, let's take a look here. Before we actually assemble the program and look at it from the GDB perspective, let's think about what each line is going to do, and then we'll try to match our expectation with the actual stuff reported by GDB. If there's a discrepancy, that means our understanding is kind of off. If it is perfectly fine, if it's exactly the same, that's good. It's confirmation that we have a good understanding of these concepts. Okay. I'll just put comments next to each line to kind of explain what it means. You should understand that already because this is stuff that we have already talked about. We just haven't really written a program to illustrate these concepts. .fill5 without actually specifying the other two optional numbers or values means I want to reserve 5 bytes, and those 5 bytes should be initialized to zeros. Okay, so 5 zeros, 5 bytes of 0. Okay, this one is going to, how many bytes am I reserving here? 4. I'm reserving 4 values. So we have 45 as a base 10 number. We have 45 as an octal number, base 8. We have 45 as a base 16 number, as a hexadecimal number. And then we have the binary number here, which is, what is the value of that? It's 11 times 2, which is 22 in base 10. Okay, I can tell it's 11 times 2 because this binary bit pattern is B in hexadecimal, which is 11 in decimal. And since I have one additional 0 as the least significant bit, that means I have to multiply that value by 2, and that means it is 22. You guys can use a calculator for that purpose if you want to. But at some point in your programming career, you really need to know how to do all these conversions. Maybe not really quickly, but at least understand how to do it. All right, so now we have an ASCII here. Well, that one is pretty easy. We are basically talking about the Ascii code of the uppercase T letter, lowercase a, and lowercase k. No big deal. And then we are getting into integers. This is where things gets a little bit complicated, because .int, each item specifies how many bytes. 4 bytes, 32 bits, okay? So now we have a problem, because how do we represent the value of decimal 45 as a 32-bit number? Oh, that's not hard at all. I mean, I know how to do that. Okay, let's do a base conversion real quick here. What is 45 as a base 2 number? No calculators. 132. Okay, what is 45 as a hexadecimal number? I'm just doing my calculations in my head real quick here. It's let's see, 2D in hexadecimal. Okay, so 2D in hexadecimal in binary is going to be 0010, which is 2, and then the D is 1101. Does anyone want to double check? I don't trust myself. You guys trust me? Okay, let's double check. Let's do base conversion just so that we can confirm that my base conversion is correct. Okay, let's do it here. I'm just doing everything on screen so that we can actually see it. So this is 1 plus 0, 2. We have a 4, we have an 8, and then we don't have a 16. We do have a 32, and that adds up to what? 32 plus 12 plus 1 is 45. I mean, if you don't trust me, you can use Excel to confirm that. Okay. All right. But nonetheless, the question is, what is this number as a 32-bit number? Well, I know what it is as a 32-bit number. It's just as a whole bunch of zeros, as leading zeros, to fill up the left-hand side, and then the right-hand side is the bit sequence that I have already specified. So we have 1, 2, 3, 4, 5, 6, 7, 8. And I'm just going to do the lazy stuff here. And then we have 0, 0, 1, 0, 1, 1, 0, 1. Okay, that's the whole number. No big deal. Any calculator can tell you that. How many byte locations do we need here? Obviously 4, right? Because we have 32 bits. Each byte is 8 bits, so we need 4 byte locations. And the i386 is a byte addressable processor. So now the question is, which byte am I going to store first? Don't you think that's a question? I mean, there are two sensible answers. One sensible answer is to say, we'll start with the most significant byte. In other words, if we want to store these 4 bytes to represent the value of 45 decimal, we will start with the most significant byte. This byte will end up with the least address in memory space. That particular way is called the Big-Endian method. Big-Endian means we store the most significant byte first. Or we transmit the most significant byte first. In other words, when you look at the TCP/IP standard, it is using Big-Endian because you always transmit the most significant byte first. The Intel processor is a little endian processor, which means, can anyone guess what we do? We store the least significant byte first. So that means when we store this number as a 32-bit number, this byte is going to have the smallest address. This byte has the next address, this byte has the next one, and this one has the highest address of these 4 bytes. It's called the little endian standard. Are we doing okay so far? All right. So the rest of this is really pretty much the same thing because each item can be represented by 1 byte. So we are just looking at a whole bunch of leading zeros. All right. ASCII is an easy one. It's basically just the ASCII code of A, U, Y, E, U, and G, followed by the null terminator. Null terminator. All right. Any questions? Now here's another idea for those of you who are creative. You can make a spoof of Terminator, and you can call it null terminator. It's a prequel of the entire Terminator sequence. Nobody's. No, you guys don't want that. I am the null terminator. I terminate strings. But this is how I can keep you guys awake. Bad jokes or good jokes, they will both work. I think bad jokes particularly will keep people awake. It's like, oh, don't tell that joke again. Yes.
Can you move the window over a little bit?
Oh, sure. Because actually, I can do a little better. Let me see if I can change the zoom here and make the whole thing fit.
There you go.
There we go.
Thanks.
All right. Okay, do we have any questions at this point? Okay, the next thing is, This program will assemble, not a problem. It will link without a problem. But how do we confirm that this is exactly how memory is organized? That's the next question. You need to know that to do your homework assignment. So the next thing we have to do you want me to keep this open? Or do you want, well, we should keep this open and then use another window for the debug session. Okay, so we'll go to the same folder, 2012 0202 cisp310, and then go to mem1, and then we have mem0 as our new program, as-gstaps-o mem0.o mem0.s. Okay, I already explained this command, so we're not going to explain that again. ld-o mem0 mem0.o. Now we have an executable. You can run it. The program really doesn't do anything. It does not fail, doesn't crash, it just doesn't do anything useful. However, when you use GDB on this program, this is where things become kind of useful, okay? Because there's a lot of stuff I want to illustrate using this one single sample program. The first thing I want to do is to say, well, Tech, you said that L1 is not a variable. Let's go ahead and print it and see what it is. Print L1, and then you go like, no debug info. But what exactly is this number here, 8048054? That is the definition of the label itself. When you refer to the label L1, at least when the program is running like this, you are referring to 8048054. Okay? What exactly is L1? L1 is the, okay, let me switch back to the first screen here. Oh, not this one, this one. L1 is actually the address of the first byte of the .field 5. That's what it is. Because it is defined to be the bookmark of the text section right before we allocate those 5 bytes. Okay? So that's one thing you have to remember is L1 is not a variable. It is a label, but the label itself is defined to be an address. Okay? All right. So print L1 doesn't really reveal, the content at that address. It just says that, L1, we don't know anything about L1. That's basically what it's saying. Well, fortunately, we have another command. Okay, just to show you the help screen of that command. That command is called X, which stands for examine. To be more exact, let me just highlight the portion. I know, this is a lot of text on the screen and it's really hard to read. So I'll just go ahead and highlight portions of it that we are reading. Okay, this is the part that we are reading out of the screen. X stands for examine memory. In other words, it's a way to dump the content of memory in a variety format. X/FMT means that the command itself is really X. You use a slash, and then you specify how do you want to display memory content. And there's a bunch of ways to display that. FMT has a repeat count. In other words, the first part of FMT, the format, can be 20, 5, 8, or whatever. You're basically telling the X command and say, how many of the following things do I want to display? The second part is followed by a format character and a size letter. The format letters basically says, okay, in which way do you want to display the content? Do you want to display values as octal numbers, hexadecimal numbers, decimal numbers? Now, under decimal implies it is going to be a signed interpretation. But if you want to use an unsigned interpretation, you can use U. If you want to display the number as a binary number, you can use T. If you want to look at a 32-bit number as a floating point number, you can use F. We won't even touch that in this class. An address, you can even disassemble a location. If you specify I, it means I want to disassemble the value of that memory location as an instruction. You can disassemble a program that way. You can use C for characters and S for string. The next one is the size letter. The size letter means especially when you're displaying values in hexadecimal or decimal or binary. Now you can specify, am I displaying a byte as an 8-bit number in binary? Am I going to display a number half word? It's actually 16-bit. So you have to remember the terminology inside GDB is a little bit different from the terminology inside your assembly language program. Because inside your assembly program, a W means 16-bit. But in here, a H means 16-bit, a W is actually 32-bit. So you kind of have to remember that. There's no easy way around this one. G is 8-byte, which is the same as a long in C. All right. So kind of looks obscure. Let's go ahead and take a look at the first 5 bytes, okay? Because we should confirm that the first 5 bytes are zeros. So the command to do that is x/quantity is 5. We want to display. Do you guys want to? Well, it's all zeros, but do you want to display as hexadecimal, octal, decimal, or binary? Pick one.
Binary.
Binary. Okay, we'll specify binary, and each item is a byte. So that's how you specify examine 5 bytes as and display each value as a binary number. Are we doing okay so far? And then most people would think, oh, okay, that's easy. Now we can just say, from where, right? Otherwise, what are you going to do? You have to specify where are we dumping this from. L1. It actually works too. That is strange. It did not used to. In the past, it did not work like this. Okay, in the past, it actually gives me something different. Okay, so it works now, which is great because you don't have to go through the really obscure thing that we had to do in the previous class. In other words, Spring 11 students had to go through a lot more trouble to get this part done. Yep.
What's that B for again? The TB, T's for binary.
B for byte, right here. Okay, so make sure you read the help screen because the help screen is very, very helpful. All right, no surprises here, do we? Okay, it says that L1 is exactly representing that address. We have 1 byte, 2 bytes, 3, 4, and then the 5th one wraps around, and they're all zeros. And they're all displayed in, guess what? Binary. Otherwise, we wouldn't have 8 digits per byte. Are we doing okay so far? Okay, so if you want to use other formats, it's pretty easy to just change the T to let's say X. Okay, now it's in hexadecimal. You change it to octal, just like that. Okay. All right. So we got that part done. No big deal. What about the next 5 bytes? Let's go to the program and look at what should be in the next 5 bytes or next 4 bytes. The next 4 bytes should be 45 in base 10. 45 in base 8, 45 as a base 16 number, and 222 as a base 10 number. Okay, so let's go ahead and see if we can display those 4 bytes after these 5 bytes. And we want to display only 4, and definitely keep the byte. But this time we have to, well, let's pick a binary too. Okay, so I'm going to display all the content of the next 4 bytes as binary. The question is, what do I do here now? L1 is starting from the very, very beginning, with a dot fill. So how do you think I should specify 5 bytes after L1?
+5.
+5. Very good. Okay. So it's an offset of 5, and here we have this thing being displayed. The question is it correct? Right. All right. Let's take a look. The first one is 45 as a base 10 number, and I did the base conversion already. The base conversion was 00101101, 00101101, so that's exactly 45 as a base 10 number. The second one is in base 8. Base 8 means each digit represents 3 bits. 5 as a 3-bit thing is 101, and 4 as a 3-bit thing is 100. So that's correct. 45 as a base 16 number means that we have 5 here as the least significant 4 bits, and then we have 4 here as the most significant 4 bits, and that's correct as well. And then we have 22. This one is easy because it was originally specified as a binary number. And we have that whole sequence back, right? 1 0 1 1 0 1 0 1 1 0. So now we have a way to display bytes like that. Any questions at this point? We have just displayed the first 9 bytes from L1. Now, if you want to, you can also do something like this. You can say, I want to display 9 bytes as binary numbers starting at L1, and it will show you, the 9 bytes. In other words, there's no such thing as a boundary based on the source code. Does everybody understand what I said by what I meant when I say that? When I said there's no boundary. In other words, from the program's perspective, from the assembler's perspective, there's no hidden boundary between these 5 bytes and the next 4 bytes. There's no boundary between these 4 bytes and the next 3 bytes, and so on. It's really just one contiguous area of memory of bytes. Okay, so that is a very important concept to remember, because when you do C programming, mentally, you form boundaries between the constructs, int x, y. In your mind, you have variable x, you have variable y, and there's a hidden wall in between the 2 variables. When you do assembly programming, you should remember there really is no such wall. Okay, x and y as 2 variables are probably right next to each other, and there's no such thing as a boundary between the 2. Are we doing okay so far with that concept? Okay. And then we have the int here. Okay, let's get through and display TAK also. Okay, so that means we have to add 3 more count to this, 12 bytes. The last 3 would be the TAK, the Ascii code of TAK. So this is K, this is A, and this is uppercase T.
Can I ask?
Yep.
In the previous command, 9 bytes, why didn't it show 8 bytes and then the last one is like something?
Because it kind of wraps around really badly here. It displays 8 bytes on the same line, so that's why the next byte, whatever is remaining, will display on the following line. Okay. It would probably be better if I use a hexadecimal representation. It looks better this way, because on each line it displays 4 bytes. And this time, because we asked for 12 bytes, the first line displays the first 8, and then the next line displays the remaining 4 bytes. Okay? So far everything is pretty easy to deal with, because whenever we define stuff with this, they're all counting in bytes. Everything is in bytes. But when we get to this part here, things get a little bit more tricky, because you have to understand what is little endian. With a multi-byte integer, which byte is stored first? That's the question. I answered that question already. It is little endian, which means it stores the least significant byte first. So let's go ahead and see if we can confirm that. What is the offset to the first byte of this particular item? Has anyone kept count?
10.
No. 12. Okay, this is offset 12 from L1. So we'll go ahead and take a look at this and say x slash, this time I only want to display 1. If you want to display only 1 item, the 1 is optional. If you do not specify a count, it is default. The default is 1. So I can just not specify the 1. And this time I want to display it as, let's say, binary. And it is a 4-byte thing, so which letter should I use to represent a 4-byte thing, a 32-byte thing? Word, that's it. Good memory, you guys are good.
T is for binary.
Oh, T is binary, that's right. Okay, T is byte. Thank you. Yeah, B is byte. L1 plus 12, because that's the offset to the first .int construct. And it's correct. If you look at this as a 32-bit number, it is 45 in decimal. But it doesn't tell you anything about little endian, does it? Because it is looking at all 4 bytes and combining the 4 bytes into a 32-bit integer already. So you can only see what it really represents as a 32-bit integer, but you're not really seeing how the bytes are actually organized. What should I do to look at how the bytes are organized?
Display in bytes instead of words.
In bytes, so there'll be 4 bytes, and we can keep it as a binary, but this time we are using B to specify a byte. Okay, so let's just kind of go over this quickly. Examine memory locations. We would want to display 4 items. Each item should be displayed in binary, and each item is a byte. Okay, and then the address, the beginning address is L1 plus 12, which is the same as the previous command. And it displays like this. Does it make sense? Now this is counterintuitive, because a lot of times people look at this and go like, it doesn't make sense. Before we have a whole bunch of zeros starting out first, now we have whatever was last is displayed first this time. But it makes perfect sense because it is using the Little-Endian standard. The least significant byte, which is this part here, is stored at the lowest location. When you display memory locations, it is always displaying in this order: lowest address, next one, and then the highest location. Yep.
Is there a purpose for that storage convention?
It's somewhat arbitrary. Okay, the advantages and disadvantages of Little-Endian versus Big-Endian is kind of an even toss. Certain things is better if you use Big-Endian. Other things are better when you use Little-Endian. The only thing is you just have to be consistent in the architecture, and you'll be fine. The Intel processors, since this is not even Intel. Since the 8080 architecture has always been Little-Endian. That's the way they store multi-byte numbers. The Motorola processors, such as the 68000 processor line, the Coal-Fire processor, and so on, they're always Big-Endian. They always store the most significant byte first. So it's basically an even toss between the two. Each one has advantages and also disadvantages. But as long as it is known and determined, it should not pose any problems from the programming perspective. Is that okay? Did I kind of answer your question? Yeah. Okay. And remember, TCP/IP is Big-Endian. So when you transmit, an IP address, or when you transmit the number of bytes in a packet, it always transmits the most significant byte first. Okay. So are we doing okay with this? Does everybody understand why the numbers look kind of opposite?
I'm just trying to make sure it's like the word that is written backwards.
It's not written backwards. It is just organized in a Little-Endian method. In other words, well, I guess in this case I chose a really bad value because it is kind of symmetric. It is not entirely symmetric. It just looks symmetric. This is the least significant 8 bits of that number. Agreed? And the Little-Endian standard says the least significant byte has the lowest address. And therefore, it appears first here when I display the number byte by byte. Is that okay? The next byte would be these 8 bits. And these are the 8 bits that we are talking about. The next one would be these 8 bits. Is that 7 or 8? That's 7. And that's 8. So those 8 bits will go here. And then the most significant 8 bits is going to be stored last with the highest address. And that's why they're stored all the way over here, or displayed all the way over there when we dump the memory by bytes.
Yeah, that's what I was talking about. It's just like the word written backwards, like the last...
They're not written backwards.
I mean, the first letter becomes the last one. And
No. No. No, because as soon as you think like that, you won't be able to do your homework assignment. And I guarantee you that. Yep.
So to go along with that, does that mean its location in memory is irrelevant then?
It is relevant.
Okay.
Okay, it has everything to do with this homework assignment. Now let's look at it just slightly differently. instead of using the binary notation, let's use hexadecimal, because sometimes it's actually better to look at things in a hexadecimal way. In base 16, the number is 2D. Okay? It makes perfect sense, because the first digit represents how many ones we have, the second digit represents how many 16s we have. 2 16s is 32, and D itself stands for 13. 13 plus 32 is 45. So it makes sense, okay? And this makes sense too because the value is only 45, so all the zeros here are leading zeros, which do not change the value that I'm representing. Is that okay so far? Does everybody agree that this is a okay representation in base 16 of the value 45 in base 10? Okay, you can always put as many leading zeros as you want, and it doesn't change the value that you're representing. Okay, now let's do this again, but this time we'll do a 4xb. In other words, we are displaying as 4 individual bytes, and each byte is using a base 16 representation. What do you think you should be seeing? 2D 0 0 0 0 0 0. And not D2 0 0 0 0 0 0. Because what you said earlier means that within a byte you also have to swap the order, and that is not true. Within a byte you keep the order.
Okay. I'm just considering like 8 zeros as the single one, as a single letter.
But it is not. It's one byte, so the bytes, there's nothing flipped here. It only has to do with the little endian standard. The least significant byte is stored first. Okay? Are there any questions at this point? No questions? All right. And this is L1 plus 12, right? Now I will go in and actually write one single instruction to load 4 bytes into a register, and then you guys have to tell me what would be the bit pattern in that register after that instruction.
Professor, really quickly.
Yes.
The pre-last line is the big endian, and the last line is a small endian.
No, there's no big endian here. This is combining all 4 bytes and display a 32-bit number in base 16. This is not Big-Endian. If I were to display it in Big-Endian, I would have separated these into 4 individual bytes too. When you combine all 4 bytes as one single 32-bit number, the endianness is not displayed anymore because it's treated as one single number. Yep.
So the Big-Endian, if displaying the last line would be the 0x2d would be at the very end.
Correct. If this were a Big-Endian processor, then the last line here would have been displaying 0 0 0 0 0 0 2D. Okay. But since this is a little endian processor, the least significant byte is stored first. Okay. Now that is going to be a very important part of this class throughout and all the way to the end of the semester. So you got to make sure that you remember what is little endian and the significance in your program. Now the significance of this in your program is it's not going to be important unless you're loading some memory content into a register or do something with memory content. So let's go ahead and just write one instruction here. And the instruction is move L, which means how many bits am I moving here? Long in programming is 32 bits. So I'm moving 4 bytes at a time. And the location that I'm moving from is L1 plus 13. 13, not 12. Okay, I intentionally put this number 13 here, and I'll put it into EAX. Okay, so this is the one instruction. This would be a good time to talk about the direct operand when we talk about different types of operand. This is the first time, L1 plus 13 is the first time that we see an operand that does not specify immediate or register. This is in fact a memory operand. In other words, it specifies a memory location. All right? Now this is also a very good time to separate the value of an operand from what it looks like. Okay? What does it look like here? L1 plus 13. Let me just highlight the portion so we can kind of focus on that part. What is L1 plus 13 as an expression? What is L1?
It's the beginning of the whole.
Select, yeah.
L1 practically is
Bookmark.
the address of the first byte of the dot field 5, right? Agreed? All right. So what is L1 plus 13?
It's the
Or 13 bytes.
An offset of 13 from that location, right? It is still an address. Now remember, all addresses are also just integers, right? You know, an address is nothing more than an integer. It's just that sometimes we can treat it as an address and say, well, don't use this value or the address itself as the value. Use the value stored at that memory location as the value. Let me say that again. When you use an immediate operand, the value of the operand is exactly what you specify after the dollar symbol. That's why it's called immediate. There's no additional step to do. Whatever you specify is the value of the operand. In this case, L1 plus 13 does not specify the value of the operand. It specifies the address at which you will retrieve the value of the operand. How do we call this operation in C? Dereference. Okay? In other words, this operand has an implicit dereference in it. It specifies an address, but the value that you're going to copy into EAX is not the address itself, but the content at that address. Is that okay so far? In fact, what we'll do here is we'll write two instructions that seem to be almost exactly the same. One has a syntax error, the other one does not. But in fact, they're completely different operands. Okay? The first instruction, the one that has the cursor at this point, specifies an immediate operand, right? Remember what an immediate operand says? Whatever the expression is the value of that operand. In this case, L1 plus 13 specifies an address, the address of the first byte of the dot field 5. So in this case, the address is going to be copied to register EAX. Because as the name implies, an immediate operand itself, whatever the expression is the value of the operand. The second line, which I will highlight now, is a direct operand. A direct operand says whatever the expression specifies. Now this expression doesn't have to be simple like L1 plus 13. It can be L1 plus X, the whole thing times 2, plus 36, and then the whole thing divided by in parentheses X 2 plus 13 plus Y. You can make it very, very long and very, very complicated. But at the end of the day, it is just an integer. But the integer itself is not the value of the operand. The integer specifies a location in memory, and the value of the operand is the value stored at that location. Is that okay? A direct operand specifies where we are going to get the value. An immediate operand specifies exactly the value right off the bat. Is that okay? Now, when we trace this program, it will be very clear the effect of these two instructions are completely different. So I'm going to save the file. Remember to save the file first before you assemble and link, because sometimes you make some changes and you forget to save it, and it will just be reassembling and relinking the old version of the program. And people have done it, again and again, and they keep asking, but I made some changes, but how come there's no, effect on the program? And not trying to find out why that is the case, they start to make additional changes to the program, thinking the first change was not effective, and then they start to make more changes to the program, and then things just goes downhill from there. So make sure that you don't fall into that spiral, because I can tell you that it's a spiral. It keeps going down. All right, so we'll go ahead and reassemble the program, relink the program, and then go into the debugger again. But this time I have to put a breakpoint at, let's see here, do a list here, list we want to put a breakpoint on the first instruction that does something useful, which is on line 15. Okay, we'll go ahead and run the program. And now we are stopped at this point. We'll take a look at EAX first. There are two ways to look at EAX. The first one is IR EAX, which actually represents info register EAX. It displays EAX in two ways. The first one is a hexadecimal number, and the second one is a decimal number interpreted signed. Okay? Now you will hear me say this again and again, and it won't make any sense until we actually talk about it. When I say signed and unsigned, I always say interpreted signed and interpreted unsigned. Now it doesn't seem to make any sense if you come from a C and C++ programming background, not knowing how numbers are represented. So we'll have to get through with number representation, or particularly how we represent negative numbers, before that becomes clear. All right. So, and if I just give you this expression, I can say print L1 plus 13. It is 8048061. Now, also the other thing you have to remember is the actual definition of L1 can change. You can have exactly the same program, but every time you use GDB, that value can change, because it all depends on where your operating system wants to put the program. Sometimes it wants to put it at a higher address, other times it wants to put it at a lower address, so we can never really count on this number being the same all the time. Okay? All right. So this number really should be the one, the value of EAX after line 15 executes. Because after all, line 15 says, look at this expression here, evaluate it, whatever it is whatever is going to be copied to EAX, right? Single step, take a look at EAX again. In hexadecimal, this is what it is, this is the value of EAX in hexadecimal. It's exactly that. Okay, any questions at this point? Does this look like anything that we have specified using the .in, .byte and stuff like that? Doesn't look like anything that we have seen so far. Okay. The next instruction is this instruction. We are about to execute this instruction. What are we going to store in EAX? We are going to the location specified by L1 plus 13. In other words, we are going to the location in memory right now at 8048061 as a hexadecimal number, retrieve the 4 bytes starting at that location, and then put it into register EAX. But EAX is a 32-bit register. That means little endian becomes useful, because the first byte at this address is going to be the least significant byte in EAX. The next one is going to be the second least significant byte, and so on. Let's go ahead and take a look at that location, byte by byte, and then we can tell what will be the value stored in EAX. That will be the X command. And there are several ways to do this. I'm just going to do it the long way first, and then we'll specify a quicker way of doing it. I want to display as hexadecimal, and each item is only 1 byte. And we'll start with just that 1 byte here. It is 00. So the least significant byte is 00. The next second least significant byte is also 00. The next one is 00. And then the last one is 25. What? Where does the 25 come from? How come 25 becomes the most significant byte? I mean, if you look at the program itself, where's my 45? Okay, this number here starts with location L1 plus 12. But remember, it's a 4-byte thing. So this one single thing, 45 in decimal, represented as a 32-bit number, is really using locations L1 plus 12, L1 plus 13, L1 plus 14, and L1 plus 15. Okay, L1 plus 16 actually belongs to the next number, the next item. L1 plus 16 is actually this guy here, which is an octal number. The octal number in binary is 010101. In hexadecimal, that really is 25. In other words, this byte, or the least significant byte of this 32-bit integer, became the most significant byte in the register after the copy operation. Getting back to here, if we single step and look at the register EAX again, what should we expect here? Just from the trace, from the memory dump a little bit earlier, what should we be seeing here? If I look at it as a 32-bit number in hexadecimal, what do you think the debugger should display?
Which is 025?
925 first.
It's 25000000. But do you understand why?
Yeah.
Now I can understand that you just kind of missed that one part, about the little endian part. But you got to understand why it is 25 and then followed by 6 zeros. Is that okay or not? It's not okay. It makes no sense. It makes perfect sense. Let me show you the way to do it, the way to look at it. The way you want to look at it is to dump out the memory, but not only limited to one construct at a time. So we'll start with, we'll display byte by byte. So we'll display, let's say, 8 byte at a time. And we'll display everything in hexadecimal, and everything is only a 1 byte at a time. And we'll start with L1 plus 12, okay? L1 plus 12, oops. L1 plus 12 is the beginning of this guy here, okay? So we are looking at the memory that is initialized based on these two items. Is that part okay? Okay. But we are displaying it byte by byte. Does it make sense? This is the least significant byte of 45, which is correct. These are all the leading zeros of the 45. This is the least significant byte of octal 45, and the rest are the most significant bytes of that particular 32-bit integer. It makes perfect sense, right? The instruction is not copying from L1 plus 12. It is copying from L1 plus 13. L1 plus 13 is this byte. But since it's a move long instruction, it's not just copying 1 byte, it's copying 4 bytes. So it's also copying this byte, as well as this byte. So those are the 4 bytes that are copied from memory into register EAX. EAX is a 32-bit register, which means we have to use the little endian standard so that we know which byte is the least significant byte, which byte is the next significant byte, and so on. Using the least significant byte of using the little endian interpretation, the first byte is the least significant byte, and that's why we end up with 0, 0 here. The next byte is the second least significant byte, and that specifies these 2 zeros here. The next one specifies the second most significant byte, which goes here. The last byte, which has the highest address in memory, is also the most significant byte in the 32-bit integer. So the 25 goes here because it is now the most significant byte. I should do that too. Use the similar ringtone. That's a cool one. Okay. So any questions about why the content of EAX becomes 2, 5, and then 6 zeros? No? No question, or this makes no sense?
No question.
No questions? Now this is all getting recorded, so you can actually play this again. But I would not just play again, listen to the whole thing again, and try to get something out of it. As soon as you encounter one part that doesn't make sense, stop there and then think about what I just said. Okay, make sure you understand, the sentences. Because this stuff can get confusing. but at the same time, it is not confusing because it's actually very simple in a certain way. Any questions? No questions? What about, yes, go
I
ahead.
have a lot of questions, but can I ask you afterwards?
Okay.
Because it's like a person.
Okay. Well, if it relates to what I just said, I would just ask you to watch the YouTube again. So if it is a question that you think is something that I did not mention, that I just neglected to mention, you should probably ask the question in the class.
No, it's stuff that you mentioned is just I can't understand it the way you explained it, so I might ask to clarify it different.
Okay. Now that's exactly why we have a debug session here, because everything that we are doing inside the debugger is designed to help you understand the concepts that I was just referring to. Okay, so you got to make sure that you understand what we're doing in the debugger and why we are seeing the results that we are seeing in the debugger. Okay?
Wait.
Yep.
So can we go back to the other terminal?
Yes. You mean the source code?
Yes. And
Mhm.
you have.
And I'll give you line numbers so you can refer to the line numbers.
So line 7.int 45, comma 045.
Yep.
So how I'm seeing it, and maybe this is wrong, but the first 4-5 are down below in the other terminal in the debug are the first 4 bytes.
Yep. This is the 4-5 in decimal.
So what you
it's a
were
base
showing
10.
us, 13, 14, and 15, that's part of the first 4-5. But the L1 plus 16, that 2-5 is the beginning of the second 0-4-5.
That is correct.
Okay.
This location is L1 plus 12. This is L1 plus 13 plus 14 plus 15.
And that's the first 45.
Yes. These
And-
4 combined is initialized
Right.
by this
That.
4-5.
Okay, and then starting at 16, 17, 18, 19, that is 0-4-5.
Correct.
Except it's little Indian, so you display the least significant first.
Correct.
Okay.
These 4 bytes, this is L1 plus 16, plus 17, plus 18, and plus 19.
Okay.
These 4 bytes are initialized or specified by the 045, which is an octal number here.
Okay.
And then obviously there's another one following that, which is just hexadecimal 45.
Okay.
Yep.
So we can put the number anywhere in EAX1 as long as we grab it from an address that's appropriate, right? Is
That
like
is
the idea?
correct.
Okay.
Okay. So that's one trick. Yep.
So in those lines, if we put in 12 instead of 8, so it would display all 3 45s.
Say again.
If we put 12 x/12 xb instead of
Yep.
8,
Then it will display those 4 bytes too.
all 3 45s.
And all 3 items in .int are now displayed. Yes. Okay.
What was he saying though? I didn't really understand what he was getting at.
I forgot his question already.
I said using the MoveL
No,
function or whatever
If we
we
were
can.
using 8 bytes, 12 bytes instead of 8, I just was wondering if it would display like 3 of these 45s instead of 2.
Okay.
Okay. Go ahead.
Oh, I said, depending on using the MoveL function or whatever command, we can choose where we want the 2-5 to end up in memory, depending on where we start.
You choose the starting point of 4 bytes that you are moving, that you're copying into the register.
Yeah, so we can, wherever we start, we can move it.
So that's the first thing you play with. Yes.
Using the label.
Okay. Next, how do we do base conversion? Because somebody asked me that question and said, but I don't know how to do base conversion. Well, first of all, I really think that in this class at this level of programming, it is probably a good idea to understand base conversion. You should be able to understand how to do it by hand. Now, I know most of you probably don't need to do it by hand because you have a calculator handy, but understanding the principles of base conversion is helpful in programming. Now, since we are all lazy, even I don't want to do base conversion sometimes, you just use print because if you look at the help page of print, you will see something that we have seen already because print can also accept a format. Okay, expression may be preceded by /fmt, Haven't seen a /fmt already? So now this is the quick and easy way to do base conversion. Print /t means I want to convert the following value into binary.
Awesome.
Or if I want to go from binary back to base 10 as unsigned interpretation, I can just punch in 0. I think it's 0b or 0t. I cannot remember. Is it 0b or 0t? 0b.
He did before. Yeah.
Okay. There you go. If I want to do base 8 octal conversion, that's an octal number. If I want to do hexadecimal number conversion, oops, yeah, my bad. Okay, so that's a quick and easy way to do base conversion inside GDB. You don't even have to get out of GDB to do all the base conversion. All right? So we have almost every single piece of information that you need to do the homework assignment, except there's one more piece. Most people should be able to pick this piece up implicitly, but I would just make it explicit anyway. In other words, I'm helping you out with your homework assignment a little more than I should. The problem with giving you the solution instead of having you guys to figure out the solution is you don't remember as well when I'm giving you the solution. Okay? But I think this one is a little bit obscure, at least at this point of this class, so I will give you that solution. Okay, let's pick, let's see here. Okay, that's a good one. What is it doing? We know everything up to line 16 already. That's just what I explained. What is this line? Oh, first of all, there's a problem with this line. What is the problem? Something is not consistent with this instruction. Exactly. Move L implies we want to copy 4 bytes at a time, 32-bit copy, and yet the destination, the second operand, specifies an 8-bit register. Don't worry, the assembler will catch it. Okay, the assembler will catch it and say something is not right on this line, and then you look at it again, oh, okay, it is not right. So we'll go ahead and change the instruction to a move byte instead of a move long. Okay, what is this doing? In other words, how are we changing the value of EAX as a whole when we execute the instruction on line 17? That's the question. What do you think?
We're changing the second least significant byte.
K in this second to least significant byte of registered EAX.
But what about everything else?
This is the same.
Everything else stays the same except for the second least significant byte. In other words, I'm doing a little surgical change to register EAX here. I'm changing 1 byte out of 4, or I should say 8 bits out of 32, and I'm not even changing the least significant byte, I'm changing the second least significant byte here. Okay? Let's go ahead and take a look at the actual effect of this line. Because once you see it in the debugger, I think it will sink in better. Assemble, ling, debug. This time we want to put a breakpoint on line 17 because we already know the first, the first few lines. This is the only line that we don't know yet. Run the program up to this point. Look at EAX 25 followed by 6 zeros. Everything is just as expected. Now we are putting the letter K. Now why is it the letter K? This one starts with location L1 plus 12. So that makes this L1 plus 11. Okay? So this is a very important concept. Everything that we specify from line 4 all the way up to line 10, they're all contiguous. There's no boundary, there's no hidden wall between those constructs. It's just one contiguous chunk of memory that is initialized according to these directives. Are we doing okay so far? The Ascii code of K is what? Well, I don't know exactly, but I can count. A, B, C, D, E, F, G, H, I, J, K. So it ends with a B. It's a lowercase character, so it starts with 6 as a decimal as a hexadecimal number. So the ASCII code of lowercase k is 6b in hexadecimal. Okay? Because lowercase a is 60. Oh, that means it is going to be what? 0. Okay, A, B, C, D, E. Okay, A, B, C, D, E, F, G, H, I, J, K. So it will be A, 6A should be the ASCII code of lowercase k. I don't trust myself. And there are several ways to confirm this. Okay, there are so many ways to confirm this. One is to say x/CB L1 plus 11. Isn't that the most direct way? After all, the move byte instruction specifies exactly this location. And the B stands for character. In other words, it's not going to tell me, the value. It's not going to display the value in decimal, hexadecimal, or whatnot. It's going to interpret this as a character and show me the letter that the 8-bit is representing. Okay. Sure enough, it is a K. Okay.
11? 11 bits is a K?
No. L1 plus 11, the location L1 plus 11 has
so it's
interpreted as a
12.
byte as a character, represents ASCII code set ASCII code K.
What's the
So it's basically 12.
What?
So is it basically the 12th one then?
What? I don't.
Pretty sure that's the decimal.
The other way to do this is to say that should also confirm my suspicion, right? Because I said the ASCII code of K is 6A in hexadecimal. 0x6A is a hexadecimal number, 6A. And I'm printing it, but I'm going to print it, interpret it as an ASCII code. So this should also display the lowercase letter K. Okay, so 6A is, lowercase letter A. Okay. See, that's why I don't trust myself.
Yeah,
Actually, you had to write it correctly. It's when you decided to drop it that it would be one
Right.
back.
All right, I just single step through that instruction. Can someone tell me the value of EAX at this point? Now remember, I made that mistake, so the ASCII code of K is actually 6B and not 6A. So given that, what is the current content of EAX?
21006800.
Exactly, because we never touched the other bytes. We made a surgical change to only the second least significant byte. In other words, it should be 25 because we didn't change it. Move byte cannot change the most significant 2 bytes anyway. So the 2500 are not untouchable by the move byte instruction. The move byte instruction has to choose one of these two. If I specify AL, it would have changed the least significant byte, but since I specified AH, it specified the second least significant byte. Okay, so this whole thing should become 25006B00. Okay, and we'll take a look at that. IREAX, and it's 25006B00. Now, when you do your homework assignment, you're dealing with a big mess of decimal number. Well, all you have to do is to do something like this. And then you convert it back to a hexadecimal number. Now, why are hexadecimal numbers so handy when you're dealing with this kind of programming?
Because hex represents binary so nicely. It does.
Okay, what is the boundary between bytes when you display a number as a base 10 number? There's none. If you just look at a base 10 number, there's no easy way to tell how the bytes are actually represented in binary. But when you look at a base 16 number, it's easy. Why is it so easy? It's base 16, and 16 is a power of 2. What is 2 to the power of what? To the power of 4, right? So that means one hexadecimal digit represents how many bits? 4 bits. All right. How many bits do we have in one byte? 8 bytes. So how many hexadecimal digits do we need to represent 1 byte. Exactly 2. Okay? And that's why it is so handy, because when you look at a number in hexadecimal, you automatically know how it is going to be represented in terms of bytes. Such as this one here, we know the least significant byte is 0, 0. The second least significant byte is 6b. The next one is 0, 0, and then the next one is 2, 5. If I were to store this register into memory, then I know the first byte that will be stored is 0, 0. The next byte is going to be 6b. The next one is going to be 0, 0. And the byte that has the highest address will store 2, 5 in hexadecimal. That is why hexadecimal numbers are so handy. Okay? Are you guys starting to see the connections, of all the little pieces that we have talked about so far? Okay? So let me just go back to the homework assignment description. Make sure I, cover everything here. I did not repeat a label is not a variable 20 times. I will leave it to you guys. For those of you who have daily prayers of some kind, integrate that into your prayer time. Along with, thou shalt not use go to and, stuff like that. But in this class is an exception. Thou shalt not use go to unless it's in assembly. You will see exactly why that is the case, because we don't have if, we don't have while. We just have jump, which is basically go to. So in this class, it's the only time you can use go-tos. But even when we use go-tos in this class, we are talking about like 2 or 3 weeks later, we are going to use go-tos in a very structured way. In other words, we're still doing structured programming, even though we are doing assembly language programming. We're still using structured programming. We're still using all the same principles that you have learned in C and C++ programming. All right, so just quickly go through these concepts again so that you can get started with your homework assignment. How memory is initialized and organized. Did we cover this? Okay, I'm certainly hopeful that we did cover that. Did we talk about little endian?
Sure did. Yes.
Did we talk about the use of the direct addressing mode?
Yes.
It looks like immediate without a $sign, but the meaning is completely different from a direct immediate operand. Did we talk about the use of register operands? EAX, AH, AL, that sort of thing. Did we talk about how a register is organized in terms of AH, AL, AX, EAX? Did we talk about what a label really is? It's not, first of all, it's not a variable. Yes. Did we talk about how to use the debugger, GDB?
Yes.
Did we talk about base conversion, 16, 8, and 10?
A little bit.
A little bit. All right. And that part too, just do it on your own. All right. So I'll go to the lab, to get started. Make sure the recording is actually there.